So if you look at what we have now in our environments, primarily indoor environments, you may say that, hey, many things that we have are becoming smart. And from a historical point of view, the development of those wonderful technologies has been largely influenced by Mark Weiser's and others' vision of ubiquitous computing that was initially described in a paper published in 1991, which is shown here at the bottom of the slide. Here's the most famous quote, and it says the most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they are indistinguishable from it. So if you're thinking about the second sentence in the year of 2021, we can perhaps interpret that sentence in a more literal sense, as technology has really started to weave themselves into the fabric of everything. And what you're looking at here is a jacket from Levi's called a jacquard, and the technology is actually from Google. And what makes this jacket unique is that the sleeve curve of the jacket is made of touch-sensitive fabric. And if you look at the phone, you can see the sensor data. And with this technology, a user can perform simple touch gestures to interact with their smartphone. And this way, the user doesn't need to pull out the phone and use the touch screen to do simple tasks like switching sounds. And all of these wonderful technologies are actually the building blocks, if you think about that way, right, of those smart environments that we have now. But if you're thinking about what else we have, there are perhaps more things that makes a big part of our daily life are not yet a part of the building blocks of the smart environments because they are not connected to the digital world. And in this sense, I think we're still pretty far away from the original version of ubiquitous computing. So an important part of my work is to enable new functionalities on everyday things by imbuing daily objects with computation. And this allows things to sense their context of use, or even I have two focused areas in my lab, interactive systems for smart everyday things and tools to help the creation of interactive everyday things. So for interactive everyday things, we investigate ways to bring interactivity to everyday things such as garments, accessories, and furniture. And we do this by enabling things, which is defined in a very broad sense, including our body or hands to sense its context of use or touch input, creating building blocks for smart environments. So you're going to see a line of technical projects, for example, in sensing to exemplify my work in this space. But I would argue that user experience can only be good if the building blocks are designed or created by people with diverse backgrounds, such as designers or creators of everyday things, as well as people with varying abilities who are essentially the users of the things. So the idea is if we give people the right and then the counterpart in the digital world are those text or video editing tools that allow people to create and share those very powerful video or web content. So you will see a line of projects that are different in nature with the focus on creating tools for people. So if you're thinking about it, the first line of my work increases the ceiling and the second line lowers the floor. And these two lines of work complete each other in some way. So now we will be turning towards the first major thread of this talk. And I will start by talking about interactive everyday things. So I'm going to cover a project which is centered around enabling things to understand their context. Let's begin with some motivation here. Things around us are mostly not smart, as we know, right? They have no knowledge about the users or how they are used by the users. For example, a cup here doesn't know what is the drink that is in the cup, and we can imagine if it knows it, the user can perhaps be reminded to not drink too much coffee based on what the user is drinking and how much cup of coffee the user has drunk. So if you're thinking about what we do on a computer in a virtual world, anything that we do is known to the computer. If you forget where you put your PowerPoint file on your computer, it helps you find it when you do a search. But this is not true for the physical world. If you left your key on your desk, but you forget where you put it, the computer doesn't know that neither. So we are investigating a twofold solution to answer this question. And our first approach is to instrument the environment, and the second approach is to instrument the user. So let's begin by talking about instrumenting environments. I'm going to use this, interactive fabrics as an example. And the reason why we would choose fabrics, because fabrics are one of those essential materials that we use to build a lot of things in the wood, right? If you think about the garments, furniture, toys, and tablecloths, and many more. But again, the problem is fabrics, they don't know anything about the user or how the users are using them. So through this line of research, we first developed an interactive fabric using inductive sensing that can sense metallic objects such as keys and coins or electronic devices. And the fabric can be used as a tablecloth to detect if the user has forgotten to take in their key. And we then developed another technique to handle non-metallic objects, such as food items, dinnerware, plastic, and then paper products. This is through capacitive sensing. And there is a paper at CHI this year in which we discuss how to combine these two approaches into a single package and allow fabrics. Thanks. So the idea of this slide is to basically show you there is another project that we did to combine two types of a sensing technique, that is capacitive sensing and inductive sensing, to sense both metallic and non-metallic object. And we implemented in a pocket form factor on a pair of jeans, so it can sense the stuff people put in their pocket. It can also mitigate some of the issues related to the reduction of accuracy due to sensor deformation when it's on a body. All right, let's move on to the this piece. So I will be focusing on sensing non-metallic, talking about sensing non-metallic objects today, and I want to motivate you a bit more through another example. So imagine if you have a table plant, if you ask a computer, and here, let's say you have Alexa, and you ask Alexa to give you advice on whether the plant needs to be watered, and you will not get an answer because the computer doesn't know that. Here I'm showing you a tablecloth instrumented with a fabric sensor, which can differentiate between dry and wet soil. So the user can be reminded when the table plant is in need for watering. And there is a notification window shown at the top right corner of the computer to remind the user whether the plant needs to be watered. And here is the notification. So, and the sensing technique that I'm showing you here is based on capacitive sensing. And when an object is placed on a fabric, our system captures its capacitance footprint, which is shown here on the laptop. And the capacitance footprint captures material as well as the shape information of the contact area of the object, which is then used to recognize objects using machine learning. And here the system can recognize an empty bowl. It can also recognize a bowl of soup. And you will see that it can recognize a slide of cheese. And lastly, it can recognize table salt. So this way the system can be useful in users' kitchen to track users' inventory of food. It can also be helpful with cooking as a virtual assistant. So what you're looking at now is the system playing a sound to remind the user what is the next step based on what the user is cooking, and after cooking, it can automatically update the user's shopping list if the inventory is short on food. So now here we have another implementation of the fabric sensor in the form of a fabric coaster, and that is right underneath the glass. And the coaster can detect the liquid inside the glass. For example, we have milk here, we have Coke, and here we have apple cider. And here we have cold water, which can be differentiated from hot water. Here we have hot water. So what we can do about it, and we can automatically update the user's diet tracking app based on the liquid inside of the glass, or the computer can, remind the user to not drink too much Coke if, it senses that the user is pouring another can of Coke into the glass. So what you're looking at here is a closed view of the fabric sensor. It is composed of a number of electrodes, just like what you have on a touch panel. And the electrodes were made of conductive fabrics attached onto a fabric substrate. And let me talk to talk to you about the sensing technique of our system really quickly. There is an object which is shown here in green, placed on top of the sensor. And here we have electrodes showing in red and blue. The capacitance among electrodes will change due to the permittivity of the object. And the black lines show the two types of capacitance in this setup. And there's a mutual capacitance and then also self-capacitance. And we use both of them. And objects made of different materials have different permittivities. And this leads to different capacitance that can be measured by the sensor. And sometimes the difference between the measured capacitance it can be quite small, so the sensor has to be very sensitive to sense the difference. And what we did was we used a resonance-based capacitive sensing technique to achieve the sensitivity that is needed for our applications. And this is a different technique from the one that we have on our phone. So what you're looking at here is the size and electrode of the electrodes and the distance between two adjacent ones. And these numbers were determined through two studies to maximize the sensitivity of the sensor for our applications. All right, so let's take a look at what are the other types of objects that can be detected by our system. And if we are here, the system can detect a hand sanitizer. This is AirPods, lipsticks. It can detect a hard drive and two different pieces of plastic cards and a figure statue. And we have a candle. And lastly, we have a book. So we conducted an experiment to measure the recognition accuracy of the tablecloth prototype, and we recruited 10 participants who were asked to place 20 objects that I just showed you on the sensor in a random orientation and locations inside of the sensing area. And each object was repeated for 10 times in a random order. And the recognition result was recorded in real time for analysis. And the machine learning model that we used in the study was a random forester, which was trained using data collected from a volunteer 3 days before the study. And this person was not invited again to the main study. So the result shows that our system can achieve an overall accuracy of 94%, which is encouraging considering that we have objects that are similar in shape, such as kiwi and an avocado. And we also tested a fabric coaster with some of the common liquids, including cold and hot water, Coke, apple cider, and milk. And we also included an empty glass, and our results shows an accuracy of 96%. But the way we should interpret this result is that the technique in its current form works in a horizontal position without the sensor being largely deformed. But as you could think about, if the sensor is deformed significantly, the sensing accuracy will reduce for sure because of the noises. And so the paper I showed you, the Pocket project I showed you, sort of mitigate this problem using sensor fusion by using the data from different types of sensors, such as capacitive, inductive, and then also resistive sensor. And it allows the system to somehow model the deformation and then react accordingly. But by no means that we have got the problem solved. If we fold the sensor, if we squeeze the sensor, it just still doesn't work. So there are much work to be done, but we're making a small step every time. So another way to think about sensing context is to instrument the user's hand instead of the physical objects, because the hand is something that we use to interact with object in the physical world. So what we did in another project was that we put an optical sensor on a user's fingertip to sense what is the object the finger touches through the texture of different objects. And in fact, many daily objects have distinguishable textures, which can be sensed using computer vision and machine learning. This way, the computer can tell if the user touches the desk or the bag or even the skin. So this enables many new applications. But now I want to pause a bit and ask you to step back a bit and think about the challenges to develop smart environments. So when I talk to people about those challenges, right, it's often the case that we start to think about, technical challenges like sensing, like device form factor, like energy consumption and such. There are important challenges. These are important challenges, but something that is often overlooked is tools to enable people to create their own smart environment. So this is the photo of a circuit that we created for the tablecloth project. And you can imagine that creating this circuit might not be easy for the folks without electronics background. On the other hand, if you look at the fabric, it's not nice looking, and likely we don't want to use it in on our table. To make it look and feel nicer is really outside of the skill set of my group and perhaps many others too. So the point is, smart environments cannot be created by people with a single set of skills. So even though what I'm showing you here is just a basic prototype. So now I want to transition into talking about tools to facilitate the creation of interactive everyday things. And then again, the idea is if we give people the right tools, they're going to create way more useful things and amazing things. And in a digital world, we have those tools that allow people to create and share powerful web and video content. And then we want to bring that to the physical world. But the problem is quite obvious. That is, the bar to creating interactive everyday things is very high. So what I'm looking at here are some of the important skills to have to create interactive everyday things. Shown on the bottom, you need to be good at electronics, materials, or even power. Then you need to understand all sorts of other things like programming, data processing, machine intelligence, and the user interfaces before something meaningful can be created as a prototype of a smart thing. So what we did was we started by focusing on one of the fundamental skills, that is electronics. And we started these two projects around 2018 and 2019. As our first attempt, we are investigating tools to make some of the everyday practices in learning and practicing electronics and the circuits more accessible to people without traditional backgrounds. And we are also investigating tools to make circuit prototyping more accessible to people who are blind or with low vision, the BLV people. So the idea is when there's an opportunity to create a smart world, it's sort of like a new world, if we can put it that way, we want to make sure that people with different abilities can participate. So I will talk about two of these projects today, that is circuit prototyping tools and accessible circuits. So, but before I dive deep into the projects, let me first show you where we are in terms of the spectrum of electronics prototyping tools that supports different needs and goals. So if you look at the figure here, we have these highly modulated toolkits on the left side, which requires less knowledge in electronics, and oftentimes they do a pretty good job serving the users who are interested in getting their job done without the need to really, dig deep into those fundamental concepts of electronics. And then we also have those, at the far right end, they are the circuits and the breadboards. And to use them, the users often needs to understand electronics quite well. And unlike the one on the left, these tools are quite flexible, and it allows the users to do almost anything that they want, right? And then, of course, we have all sorts of other things in the middle to serve different needs and goals. And we started our work from the very right side, that is the circuit and the breadboard. Because in comparison to the other options, we think breadboards and circuits are extremely unbalanced in terms of flexibility and accessibility. They're very flexible and they're very powerful, but very hard to use for novices. So in this first project, we investigated how do we use software to lower the entry barrier to learning and practicing electronic circuits using breadboard. And we first investigated the challenges that the novice learners encounter, and we identified some of the common mistakes that novice learners make. And one of the examples is missing electronic components, such as forgetting a resistor when creating an LED circuit. So if you're thinking about it, if you don't have a resistor here, for most of the case, probably you will get the LED burned, which is not something that we want. Right. So to address this problem, we created a system which borrowed the concept of autocomplete from text editing software to provide suggestions about what and where an additional component can be inserted into the breadboard to make it a functional circuit for the existing component. So one of the examples here is that if the user drags an LED to the breadboard, and the system shows the user a semi-transparent resistor as a suggestion to complete the LED circuit. So when the user sees the suggestion, they can either take it or ignore it, but at least the chance for the user to burn that LED accidentally becomes much lower. And then also, the user doesn't need to, spend time reading data sheets, which are pretty hard to understand, right? We know that. And here in another example, you can see that a potential meter is suggested to complete an LED display circuit. And from our study, we learned that the potential meter is something often missed by even expert users. And you may have noticed that, here the circuits are created using software instead of, those physical components in a breadboard, right? So this is something you will see, I believe you will see more and more, and people started doing. Software tools and have a lot of benefits at the early stage of circuit design because the user essentially doesn't need to, keep an inventory of electronic components, which may have, all sorts of different types and values. Like if you're thinking about ICs, resistors, and capacitors, right? So it can create a lot of mess, and this is actually a common barrier for novice people who begin to build electronics. And then also the second point, if you're thinking about the features like copy and paste, redo, undo, tooltips, and also auto-complete, they have made a circuit prototyping through software in an efficient and effective and less error-prone experience for novices. And then also the last point is that the virtual circuits can be easily stored, documented, and shared among different users and groups, and even across different locations via the internet. It won't be as easy using a physical breadboard. So despite all these benefits, the major drawback of using software is very clear. That is the disconnection between the virtual and the physical world. And this becomes an issue, as you can imagine, when when prototype interactive things, including sensors and actuators, as the user typically needs to interact with the components physically, right? And of course, in the real environment. So what we did to address this challenge was that we created this Arduino shell, which serves as an interface between the virtual and the physical world. So the user can use the physical I/O component, such as a piezo or a motor, as a proxy of their virtual counterparts in the software. What you're looking at now is that the user specifies that the virtual piezo has a proxy, and now the user inserts the physical piezo on the shell. And they repeat the same thing to specify the proxy for the motor. And now they connect the motor to the shell. And the physical proxies themselves behaves as though the entire circuit created virtually is real because we have a circuit simulator running under the hood. And on that shell, we have pre-installed all sorts of basic components, such as valuable resistors that are needed in most of those simple circuits created by novice learners. And using this approach, the user can now really interact with virtual components physically. And what's also nice about combining the virtual and the physical world is that we can, take advantage of both sides, right? For example, two people can design a circuit together remotely, which is not possible in a physical world. And one person can even virtually borrow a physical component from a remote site. So here we have a novice learner working with a remote instructor who is teaching her how to construct an LED circuit. She has an LED, and the instructor on the remote side has a flex sensor who can bend the flex sensor and demo how to control the LED that is on her side. And this happens in sort of remote collaborative environment, right? If you see and that person bend the sensor, the LED turns on. So that is circuit prototyping tools. Let's move on to the accessible circuits project. So the goal is to design the right tools for people with different abilities so that they can join us to create the smart environment. And this is Dr. Joshua Miali, who is a blind engineer from San Francisco, who spent entire his career creating electronic devices and tools for improving accessibility. So it's not a surprise blind people can actually create electronics, but the floor, as we can imagine, is really high. Blind people, BLV people, needs practices a lot, right, to do what Josh is able to do. So in general, the prototyping pipeline from reading circuits tutorials to creating and debugging circuits are still largely inaccessible. And despite that, some efforts has been made by our community. So after reviewing some of the literatures, we first attempt our first attempt was to address this problem in this space was to make tutorials accessible. And we focused on online tutorials that are widely used by novice learners. And here I'm going to talk about the Tangible Circuits project. So there are three underlying questions to understand the problem and to solve the problem. So the first question is, what are the current practices and needs for online tutorials for BLV people? And the second question is, what is the magnitude of the accessibility limitations within online tutorials? And the last one is, how can we develop a solution to mitigate the limitations? So let's look at the first one, the current practices need for online tutorials for BLV people. So to address this question, we conducted a series of semi-structured interviews with 3 BLV engineers who are familiar with circuit prototyping technology. We found that navigating circuit implementation was really hard without the vision due to the cognitive load that is required to understand the circuit diagrams described using text and also a screen reader. So what you're looking at here is a circuit diagram, which describes how the components are connected, and also the location of the components on the breadboard and the spatial layout of those components on the breadboard. And of course, the shape of the breadboard, shape of the components, right? So again, they are very hard to understand without the vision. So the second question is, what is the magnitude of these accessibility limitations within online open source tutorial platforms? And for the purpose of this study, we collected over 3,900 online tutorials from 2 popular open source tutorial platforms, Arduino Project Hub and the Frixent Hub. And these tutorials were then analyzed using Web Content Accessibility Guidelines, or WCAG guidelines, which is an online protocol and a guideline system for ensuring web accessibility. And what you're looking at here is a figure detailing some of the findings from our analysis. Now, overall, we found that the majority of these tutorials were woefully lacking in terms of accessibility to people from the BLV community. For example, we found a large portion of these tutorials contained visual graphics, including circuit diagrams, schematics, photos of components used in the circuit project, but very few contain any sort of circuit description or written step-by-step instructions to allow the completion of the circuits. And in fact, only 2% of the tutorials surveyed met the WCAG standard of accessibility, which indicates significantly limited accessibility in those online tutorial platforms. So informed by the insights from our formative study, and we try to answer this third question, that is, how do we develop a solution to mitigate all these limitations that we just identified? And then we developed an audio-tactile tutorial system called Tangible Circuits using 3D printing and the touchscreen devices for audio feedback and also sensing input. So the key here is that we don't want to create something crazy. We want to use something that perhaps can be well accessible to the community of the BLV people. So in Tangible Circuits, circuit components and the wires are printed using conductive filament to allow for touch-based interactions using audio annotation. And this allows users to learn how the components are connected and how they are laid out on a breadboard and feel the shape of the components as well. And this is how it works.
Just to say that we can't hear the audio.
Oh,
sorry.
Thanks for letting me know. My bad. I should have clicked that checkbox. There you go. Let me restart the video.
This is NPN transistor. This component should be inserted into pin 19J, 20J, and 21J. This is wire line 4. It connects a buzzer to an NPN transistor. This wire should be inserted into pin 13H and 20H.
All right, so to understand the effectiveness of Tangible Circuits for assisting BLV users at understanding simple breadboard circuits, we conducted a formal user study. And our study consisted of 2 sessions, learning and testing, as well as 2 conditions, Tangible Circuits and the web tutorials. And in the learning session, participants were asked to learn one of 4 sample circuits using either tangible circuits or web tutorials. And we modify those web tutorials to meet the WCAG accessibility standards. And the testing session followed the learning session immediately, in which participants were asked to complete an error identification task. So in that error identification task, we presented the participants with a complete circuit using physical components and an unpowered breadboard, like the ones shown here on the slide. And the ones on the left are simple circuits, and the ones on the right are a little bit more complicated ones, as they contain more components and wires. And then each of these physical circuits was similar to the circuit described in the tutorial, but contain a wiring error and a component error. And a wire error involves either a misplacement or a missing wire, and a component error comprises a missing or replaced component. So we artificially insert some error in it. So this is the success rate, and overall participants performed significantly better with tangible circuits for both simple and complex circuits. And then we also collected Likert results in order to gain insights of the subjective experiences of our users. And we found overall, on a scale of 1 to 5, participants found tangible circuits to be less confusing, less frustrating, and more helpful for understanding information than the web tutorials. As we noticed that the circuits that we tested in this study are relatively small and simple, right? So in reality, I think circuits can be way more complicated. So something that has to be done is, a little bit more research and then also study to understand whether this approach actually works for more complicated study in sort of like a real world practices. So I've talked about 2 focus areas in my group. In the first area, I showed you examples to make fabric objects or fingerprints to sense its context of use. And these are the building blocks towards smart environments. And in the second area, I showed you some of the work that I have done to create tools to lower the entry barrier to create electronics and smart environments for people who do not have technical background or strong technical background, and those who do not have a healthy vision. And the projects that I've shown you today are diverse in many different ways, but they are, kind of united under this common and a very broadly defined goal, that is, again, to create a better user experience in smart environments. So here I'm showing you this figure again. The reason I want to show you this figure is because I want to tell you some of the future research of my group by using this figure. So we have been thinking very hard about how to create interactive smart things and user interfaces by starting to gradually involve people with diverse background in our design and innovation processes. And this is where a lot of collaborations can happen, right? So on top of that, we will increase our impact by working with people in different application areas, and like healthcare and education and many more. And a big part of our work will continue to focus on making electronics more accessible, but we will expand our work to power and materials to make fabrication process easier, to make these, even make those battery-free systems easier to build, right? If you're thinking about it, I've been talking about this bottom-up approach by looking at those very low-level steps, right? I've shown you tools to help people to create electronics. And I think maybe there are more people from the other side of the spectrum who wants to get the job done, who wants to build smart environments, smart things without really digging deep into these low-level stuffs. So what we did was we just started a project to take an opposite approach, and where we look into how to embed sensing power and a little bit of a computation into the infrastructure of home and an office environment, like floors, like walls, like ceilings. And our goal is to allow people to create smart home and offices using smart infrastructures without the need to have any knowledge in electronics and computing. So the idea is anyone knows how to renovate their home by going to Home Depot, which is a home improvement retailer here in the States and Canada. They should be able to, create a smart home environment. And I hope this gives you a little bit of idea of where we're heading. And the project I show you have attracted some good attention from the public. And then, of course, nothing can be done without this group of wonderful PhD students and the collaborators. And thank you for your attention.